Hello everyone, it's September the 4th. Alright, let's take a look. We had a difficult one yesterday, most likely going to get a difficult one today too. Sum of distances in tree. There is a undirected connected tree with n nodes labeled from 0 to n-1 and n-1 edges. 1, 2, 3, 4, 5. You're given the integer n and the array edges, where edges I equals AI, BI, indicates that there is an edge between nodes AI and BI. Okay. Return an array answer of length n, where answer I is the sum of the distances between the ith node in the tree and all other nodes. So given n is 6 edges, we have 0, 1. What, does this I mean anything? Just indicates there's an edge between nodes AI and BI. I don't think AI, BI means anything. It's just these are the edges, right? So don't get confused. Just 0, 1, 0, 2, 2, 3, 2, 4, 2, 5, right? So the answer is 8 for the ith node, so the 0 node. We're going to have the sum of the distances between the ith node in the tree and all the other nodes. So from this node, we have 1, 2, 3. No, it's the sum of distance. So sum of this and this is 1. That's 1, right? So that would be 2. This is 2, so that's 4. This is 2, that's going to be 6. And this is a 2, that's going to be 8. So that's 8. And looking at node 1, well, node 1, we have 1 here, 2 here, that's 3. That's 6. That's 1, 2, 3, that's 9. That's 12. Okay? So the third one, we have 1, 2, 3, 4, 5, 6. Okay? So all these three are the same because they have the same topology, right? So this one will go 2, 2, right? That's 4, and 5, 6, 7, 8, 9, 10. So they're all 10. Oh, it actually tells you how this is. Okay. So n is 1, no edges, so output is 0. Okay. The given input, so they do not point into themselves, and we have 3 times 10 to the 4th. Interesting. Alrighty. Distance, right? Distance. So if I compute the distance, I can use DFS to compute the distance from one node to all the other nodes, right? So let's say if I want to know the distance between 0 and 1, that's the same distance as from 1 to 0, right? So if I find the distance from one node to another node, I also find the distance from that node to this as well. So let's say I go from 0, right? And I find the 0 to 1 is a 1 distance. So I can record that as, I put that on the 0 and put on the 1. And then I find 0 to 2, I put on 0 and 2, right? And then I find 0 to 3, right? And to find 0 to 3, and yeah, let's say we'll find 0 to 3, then I can do that, 0 to 4, 0 to 5. So that's all good. So we can do on both. And then I start from 1 to 2, right? But the thing is, when I compute, like if I want to do this, it's going to be O(n) squared, right? Because from each node to everybody else, I have to visit every single node. So that's O(n). And they're telling me that I have to go from every node. So that's O(n) squared. And then given that's 3 times 10 to the 4th, we cannot use O(n) squared. So we have to be a little bit smarter, right? Which means when we do one DFS, we actually already know the distance. Actually, we know the distance just by looking at this, right? Like 0 to 1, if we have an edge, so that edge already tells us that the distance between this, right? So we have all the one distance, they're all done. What are you saying? Like we go from like, can I tell the distance between 1 and 2 is going to be 2 by knowing 1 to 0 and then 0 to 2, the distance between these two? How do I know that? Well, I know that because, let me think. I mean, in this case, right, if I want to calculate the distance between 1 and 2, and I know 1 will go out to 0, so it's the same as calculating the distance between 0 to 2, which I already know, right? So if I want to know 1 to 5, it's the same as to know 0 to 5 plus 1 to 0, which means if I know how, and it's connected, right? It's a connected tree, which means I can reach any node from any other node, right? So if I do one traversal, it doesn't matter which node I pick. I can pick 0, so I have the distance from 0 to every else, right? If I have a node, if I go from 0, and I know 0 to 1, 0 to 2, all the way 0 to 5, right? I know all that. Now I want to go finding, and by doing this, we also already know 2 to 0, 5 to 0, 4 to 0, right? So the next round when we go, it's going to be, I want to calculate 1 to 2, right? And then 1 to 3, 1 to 4, all the way to 1 to 5. And then 2 to 3, 2 to 4, 2 to 5. That is still O(n) squared, if you think about it, because, but we can know, it's like, if I go 1 to 2, it's the same as 1 to 0 and a 0 to 2, right? Actually, it's not. Like, if I want to say 2 to 4, I won't say it's 2 to 0 and then 0 to 4, right? That's not true. That's not true. So, is 0 always going to be the root of this? Not necessarily. I can definitely see that it doesn't have to be. I mean, it doesn't have to be. 2 can be the root. And every node can be the root. Root doesn't really matter. Okay, so let's think about another way. So when I traverse, right, 0, 1, 1, 0, right, 0, 2, 2, 0, that's fine. And then when we traverse, so if anyone can be the root, and as I traverse, we go for the thing that we have not hit yet. Like, let's say 0 we visited already, so like we're talking about regular DFS, already visited. So when I'm at 2, right? When I'm at 2, I know that, what do I know? Like, if I am at a node, right, and then there's some traversal already happening, and I want to know the sum of the, like, basically the distance to everybody. Distance to everybody else. So I will know, right, from a node point, right, if I'm in a node and I have a bunch of children, right, so a bunch of children, so I know to all these children the distance is 1. So now the question is, what is the distance to the rest, right? So if I'm at 2, I know 0, 3, 4, 5, they're all 1s, right? And then I need to find out the distance between myself and the ones that's 2 levels out. 2 levels out? Huh. How do we do this? Yeah, I'm at 2, so I know I have 0, I have 3, I have 4, I have 5, right? And the recursion is giving me a root, right? The recursion is giving me a root, then find me the sum to everybody else. That would be pretty hard to do. If it's giving me the root and find me the distance to everybody else, right? Then I can find the distance to, let's say, giving me a root, I'm at 0. So I first find all the distance of my immediate children, right? Those are good. And I can anyway, so like I have these distances. And then to find the distance to the rest, it'll be the distance like from 1 to the remaining children, right? That does not go through myself, and those will be adding to this. So I need to find all the distance that's starting from 1, excluding 0. Yeah, and then to know 0 to everybody else, I need to find all the distance of 2, starting from 2, that does not go through 0. Okay, and now I'll go to 2, and I can say all the distances that starting from 2 that does not go through 0. Huh. Oh no, man. How does this one work? I mean, we cannot just find, like, there are so many paths, right? There are so many paths. Hmm. If I'm at 0, right, I want to find the distance to, let's say, to 1, to 2, 3, 4, 5, right? And I find the distance to 1, but I need to also look into 1, and the 1 doesn't go to anywhere. So that one is, so I'm looking at a 1, and 1 I want to find a 1, 2, 3, 4. Now 0, 2, 3, 4, 5, right? And then I can find 0, and then we go look to 0, 0 to 1, already found it. So that's one I found it. So we need to look for 1 to 2, right? And 1 does not have children. So 1 to 2 I cannot do. I have to wait for 2. So to find 1 to 2, I'll have to how do we handle this? Alright, so 0 to 1 is same as 1 to 0. Right? So if I find 1 to 5 is same as 5 to 1. It's an interesting question. How about we do it? What would BFS work? Right? 0, let's just say that's the root level, and then we go to the second level, right? Then we have 1, 2. That means this and this is all 1. Then we can handle that. All right, and then normal level here, and then from 2 we have the third level. So now our distance is 2. Our distance is 2, right? So when we handle this, right? When we have a node, I have a bunch of kids. What we get is from the root to all the children we have, and then from these children, because they're on the same level, so they get connected through that root, right? They get connected. Well, what is a distance? What is a distance? I guess it should be the shortest, right? Yeah, it's 0, 3. You're not gonna go and then go 3. So this should be the should be the shortest. So connected. But what if, like, say, 1 and 2 is connected? Is there like a loop? No, it's a tree, right? So I think tree means there's no loop. A graph can have a loop. A tree, I think, is no loop. Is that true? A tree has no loop. Wait, what's the definition of a tree? So a tree versus a graph. What is the difference between the two? So a graph of blah blah blah. Find a set of one-on-one nodes such that there is a specially designed node as a root, partitioned disjoint sets hold on. Nodes and edges. Each node have any number of edges. There's a unique root. There will be no cycle. Yeah, so this is no cycle. Tree has no cycle, and we do have a root. I didn't really say where the root is, but it doesn't matter. We can pick anyone as a root. But there will be a root, and there's no cycles, right? No cycles. So when we hit the second layer, right? So if we go layer by layer, when we hit the second layer, then the distance between the nodes within this layer, within the second layer, when they're connected to the root, will be all like 2, right? It's 2. So once we have that, we have a root and a bunch of kids, and the distance between all the kids, like all the combination of kids, will be like everybody to everybody else, right? Everyone to everybody else. So like 1 to 2 will be 2. And of course 2 to 1 will be 2 as well. And if we have some like others, then 1 to that will be also. And 2 to that will be as well. Okay, so that's second level. Now we go to the third level. So one of the root, one of the child, it's another root, and then we expand. Again, we do the same game. All these are 2's, right? So 3 to 4, 3 to 5, and 4 to 5. And they are or 2's. But then if we want to compute, let's say 3 to 0, right? 3 to 0, which means we're trying to find the distance between a grandchild to the grandparent. So the grandparent to the grandchild, the distance is the level. So grand to this is distance of level. So we need to know the number of so we need to know the levels, right? And we need to know the number if we have a bunch of grandparents. So all of them to this will be, okay. Then on top of that, the grandchild to the uncles and aunts, right? This is like the uncle. That's the parent, and that's the uncle. So that to the uncle will be 1 plus this, the distance between this to the uncle. Okay, so in that case, what are we saying is for each level, right? So when we reach a new level, right? We reach a new level. We first compute the distance between the siblings, and then we can compute the distance between the parent, which is easy, between the parent. So like we go one level up, we could compute that between the parent, and then we compute that with between this and the sibling, between this and the uncles and aunts, which can be done, and then we compute that with the grandparents, right? And there's no, right? There's a thing that I can compute with this grandparent. If I have another grandparent, right? If we extend this thing, if I have another grandparent, how do I know which grandparent I'm gonna? All right, so I can say, okay, I find my father, I find my parent. It's not father, mother. I find my parent. Yeah, because that's where I get connected. I find my parent, and then what I need to know is the distance between this parent to everybody else. That we have already computed, right? That we have already computed. Yes, that we have already computed. Because what we assume is at each level we compute the distance between the child to all the siblings, right? We know all that, and we know the child to all of the ancestors, right? So if we have that, then from the child to all the ancestors, because the child gets access to the ancestor from the parent. So, and the parent knows everybody above, so I just need to get everything that the parent has, and then we can just add 1, that will be this. And remember, what we want is the sum, right? Not really the sum, we want the sum from each node. So what we're saying is we can compute this to all the siblings, but we are not computing this to its children. So we know the distance from this to all the siblings, right? And we know the distance between this to all the ancestors. And we can combine them together, right? That's what we want. We can combine them together. So if I know the distance between 2, right, this parent to all the ancestors, and is parent to all its siblings, then that sum plus 1, oh shoot, that's not plus 1, that's the sum, because they have to plus 1 to every single thing, right? So it's the total number of nodes, that we have encountered so far, right? Plus the sum of this to everything will be the sum of path, the sum of distance from 3 to all the ancestors, right? And then 3 has also plus everything, or the distance between 3 and all its siblings. So we now get the distance between 3 and everybody else, right? But at the same time, we have to increment 2 as well, right? Like, how do we get from 2? So we know 2 to its sibling and 2 to the ancestor. How do we get 2 to the next, to like for each level, right? All these has to update as well. That is interesting. Oh, it can get update, right? So because, no, hold on. Because I get, because we want to get a sum. That means we cannot get a sum. We need to get every single one, right? So if I have every single one from 2 to all these ancestors and siblings, right? And when at the 3, I want to access them. And I access the 2, access its parent. And that's fine. And we get a parent. And I want to access 1, right? So we look at 2 to 1, which is 2 distance. So plus 1, that will be 3 distance. That tells me the distance between 3 and 1 is 3. So I add that to 3, and I will also add that to 1, right? So now we have 1 to 3. So it's always mutual. It's always mutual. So I have to go through every single node that has been encountered before, right? Every single node that has been encountered before. And we cannot do a sum. That feels, now looking at this, 3 times 10 to the 4th. Like for each node, I have to go through the entire thing. Oh, I don't have to go through the entire same thing because all these have the same structure, right? All these have the same structure, which means when I compute 3, right, I go through everybody. And then when I say I go through everybody, I say I can create the distance between, let's say 3 to 0, 3 to 2, 3 to 0, 3 to 1. So the distance between 3 to all the ancestors, right, is the same as the distance of 4 to all the ancestors, right? And also 5 to all the ancestors. So that means what we need to do is what we need to do. So what I'm saying is at any point, I know the distance between, at each level, I know the distance between the one node to all the other nodes, right, on the previous level. So now I have a child. When I have a child, I am able to know the distance between this one with everything on the ancestor. And of course this one to everybody else. But let's focus on the ancestor first, right? So we know this one to everything, and that is going to be, oh wow, are we going to keep a list for every single one? Are we going to keep a list to every single one? Oh man, if we keep a list, like not the sum list, but actually individual. Like if we don't keep a list for individual, how do I know the distance between 3 and 1, right? Because to know the distance between 3 and 1, I need to know the distance between 2 and 1, which means I have to keep the distance between 2 and 1, right? I cannot just have the sum of the distance at 2 and all its ancestors, because that's not going to work. I need to know the distance between 2 and 1, which means I need to know the distance from 2 to 0 and 2 to 1. Can we represent it better? So it's going to be a n by n matrix. N by n matrix. Okay, it's an n by n matrix, and yeah, n by n matrix. So the row column, the 1, 2, and 2, 1 will mean the same thing, right? 1, 2, and 2, 1 will mean the same. So it's just going to be like top half, the top half. So I'm going to look into the top half, 2 and a 1, right? When we get that, so we know 3 to 1, right? We know 3 to 1, and I can record it, right? And also I need to know like all the nodes that have been experienced before. So I can get 3 to 2, right? And then I found 3 to 1, I found 3 to 0, and I record all of them. And as I record, because it's a matrix, it's updating 1 to 3, 0 to 3, and 2 to 3 as well. Okay, so 3 is done, I get all that, and we'll also do 3 to 4 and 3 to 5, which they will just be 2, because they are on the same level. Alright, so when 3 is done, now we'll look at the second one, which is 4. And we're going to do the same thing. So we look at 3 and 4. Oh, that one is done, so we don't do that. And then we want to know 4 to 2. That's good, updated. And then 4 to 0, which, this is 2 to 0. And then 4 to 1. These are all 1, right? So at each one, we can compute the distance between this and everybody else, right? But this and everybody else. Okay, so we're good with that. And when we want to calculate the total value, I am just going to sum up every row. So let's just make an n by n matrix then. An n by n matrix, it has to go n squared. I am pretty sure there's going to be an easier way. Like if we want to do 4 and like 4 to 2 and 2 to 4, right? Yeah, like every time we just update 2 things, like ij and gi, we updated 2 things. Yeah, I think it will work, but honestly, the time complexity is just, I'm going to try this. I think it might work. So, all right, where are we? This is what we're going to do. All right. So what's on my mind is, well, for one thing, we need to turn edges into the tree. All right. So we know where to start. We know the because we need to do traverse. So from each node, we denote its parent. So we need to know its children. So we're gonna first turn edges into a tree, right? So tree is going to be this for this in range n. all right? So everything is going to be a list. And then what we're going to do is for AB in edges, right? And we're going to say tree A dot append B and tree B dot append A. So that will turn the edges into a tree. Now we have the tree, now we need to have the distance matrix. So we're going to say a dist, right? Dist mat equal to 0, right, times n for this in range n. So that's an n by n matrix. So now we have n by n matrix. So now we're going to do breadth first search. So for breadth first search, we need, what do we need? We need a Q. So the Q is just going to be the root. We're going to say 0 is the root, and we need a scene, right? The one we have seen before. So scene is going to be a set, and 0 has been seen before. Now I'm going to say while Q, right? And temp is the next level, and next one is for node in Q. So everyone is pop out. So now 0 gets popped out, right? So 0 gets popped out, and 0 to itself is a 0, right? So 0 pop out, we don't have, so 0 already, we have computation, like current ready from 0 to everything. So now we need to do is to find the temp, right? So we have the node. So we're going to say for child in tree node, right? Tree node. And for each child that's not been seen before, so we say if child not in scene, right? If child has not been seen before, then what we're going to do is, let me think. Because it's a tree, so the siblings are not connected, right? Therefore, we don't even have to, we can just set a set, and every time we visit, we can put it in. So I think that will make it a little bit easier for me to reason. So for each node, right, coming out, that's when we visit the node, right? We visit the node, and we put the node into scene. So in scene.add node, right? We put the node in the scene, and then we find the child, right? So for the child, for all the child, right? And then for all the child in the node, if the child is not in scene, if the child not in scene, then we say temp.append child, right? And this one will get, what we want is the entire level, but there's difference. There's difference because if we have another one here, right, and then they have children, and the distance between this and this, how do we compute that among the siblings? If the siblings share the same parent, that is easy. If we are on the same level, but they do not share a parent, and they will share a grandparent, right? How do we compute that? A grandparent, which means, that is an interesting question. Hold on. That one actually I haven't solved yet. So I'd imagine we have another one here, and this one has some children as well. How do we compute the distance between this and this? Well, we can compute, we can say we need to know the distance between this and this, right? But we do not know. So what do? Right? We don't know this to this yet. Because we want to know this and its siblings. That's the premise, right? We know this distance between this and the siblings. So its and all the siblings. And if we have something here, right? Which means, hold on. If I have a list of all its siblings, all its children, right? And so we're popping on this one out. This one is still inside. Inside the queue, right? We don't know. And then what we calculate is the distance between this and everything that it has, right? So this two, yeah. So this one and all its siblings, right? So we get all that, and I'll calculate this to all that, but we don't know these siblings yet. But that's fine, because when this one pop out, I will have to calculate from this one to this, because these are seen, right? They are seen. Now when I calculate this to this, because they are seen, I'm just going to calculate this between its parent to this, which is computed from this to its parent. Which means for each child coming out, we don't push into the temp. Oh, in that sense, we do not add the node at this level. We do have to say it here, right? And then for child is not in scene, we need to put the child. No, we don't put the child in scene yet, so we have the first child coming out. I need to know all the child that belongs to, which means we're gonna have another temp, right? So this one is gonna be, let's say next level, right? This is next level, and for each node, I need a temp, right? Let's just call it children, right? Let's make children. And then if child is not, basically we just picking out the children, which we can actually do. Let's say children equals child, right? So maybe child for child in tree node, right? If child not in scene. So this is the children. Now when we get the children, we need to compute the distance among the children, right? So what we're gonna do is for each child, so we're gonna say for child in children, which just be for child in I just realized this is hold on. Because I need to also find this between this one and everybody else in the child. All right, how about we worry about the siblings at the end? Let's worry about each one to all the ancestors first, right? Let's say for child in the children. So if we get every child out, and then we go through all the scene, right? And then we do that. So actually we can just say for okay, let's say for child in tree node. I don't call it parent, but it's fine. So for child in tree node, right? If child not in scene, now we're gonna compute everything that the child can connect to. So we're going to say for parent in scene. So everything in the node that's in the scene, they are parent, right? And so for all the parent in scene, what we're gonna do is we're gonna say dist map, right? Dist matrix from the child to scene, right? Well, equal to okay, so hold on. What are we doing? What are we doing? We're trying to figure out, right? We're trying to figure out. So for each child not in scene, what we're gonna first do is dist map child to node, right? That's its parent. That's not called it node. Let's call it parent. And all the node is going to be parent. For child to parent equal to 1, right? And then for sure dist map from parent to child is going to be 1 as well. And then for all the ancestors, this is going to call ans in scene. But that include the parent, right? That include the parent. Have you added a parent? No, parents already added. How do we handle that? So we handle that by for everything in scene, right? And we just skip the parent, like we say, if ancestor is not equal to parent, because we already done the parent. So if it's not equal to parent, then we say dist matrix child to this ancestor, right, will equal to actually it's fine. We don't have to define it here, right? I think it's fine. We can just say if ancestor is not equal to parent, then dist map this will equal to dist map child to parent, which is 1, plus dist map parent to ancestor, right? And then else if ancestor is the parent, so we say dist map child to parent will equal to 1, and of course this one has to be double it. So we're going to double it with ancestor to child will be the same thing, and this will also double it, right? So we double it to parent to child. Now what I'm thinking is parent to parent. They are 0. Parent to parent is always 0 because we initialize with 0, which means this do not apply. We don't have to check. There's no need to check because parent to parent, right? If parent is ancestor, then we just do parent to parent, which is on the diagonal. And diagonal is always 0. So we can just directly do this, right? So that's from each child. We are finding this one to all the parents, right? Everything. We get everybody. Now, once we get everybody, right, what do? We that's it, right? But we don't add. Do we add this to scene? Actually, we can, because this is like an ancestor, right? Like, if we do this one first, all 1 sees is 0 and everybody else. And then if we add 1 to the scene, then 1 becomes an ancestor 2. So to find the distance between 1 and 2, 2 will say, I want to find the distance between 2 and 1, so that's going to be 2 to 0 and a 0 to 1. Yeah, that's actually cool. So if child not in scene, we compute everything, and because it's double, right? So it's fine. And once it's done, right? Once it's done, we're gonna add scene.add child. We add child to the scene. So when the next child pops up, the previous child becomes an ancestor, right? An ancestor. So we are going to process this entire thing, right? The entire thing for every child. So we make this computation, and once it's done, then we pop the other parent out, right? And when we get every children of that parent, then everything becomes ancestor. So these all become ancestors, which is fine because the tree just you can change your view. They are the ancestor, and then the distance between this one to this, it will ask for this to this, which we already computed when we compute 2 to that. So that's fine. Now, the next question is the next level. So here's where the next level comes in. So we're going to say next level dot append, right? Child. So the next level, every time we finish a child, we're pushing in, right? We're pushing in, pushing in. Once we're done with everything, so Q exhausted, we just say Q equals next level, right? Q equals next level. Now go back to the Q, and then we go to the next level. And if a parent, like 1, right, a 1, it doesn't have anything to give because everything that it connects to is already seen, now we just don't compute it, right? And then once it's done, and the matrix are populated, right? All the matrix are populated, so we're just going to return, right? We're going to return this. We're going to say for row in distmat, we're just going to sum row, and that shall be the answer. All right, let's give this a shot. We have first test case, and it's 6. I'll copy and paste in this. All right, and then the answer is this. Okay, all right, so here's what we're going to do. We're going to change all this. All right, and then we're going to change all this. All right, and the second one is an edge case. 1, so no edge, so return 0. The next one is 2, and then we have 1, 0. And this one shall return 1 and 1. All right, this one will be n edges. This one will be sum of n edges. Hold on, I have a message. Wow. My girlfriend just ordered a banh mi sandwich. A vegan style. Suena muy, muy rico. Alright, so edges. Oh, I taught her. Oh. Me olvidé. Decirlote. All right, let's go back to this end and edges. All right, let's try it. We all pass. Now, I think this is correct, right? But the only worry I have is time complexity. This is going to be like this is all in square. Even if it's let's try it. Submit, pending, judging. Yeah, so it's TLE, a very fast TLE. It's so fast. So it's yeah, I was afraid it's gonna be TLE. It's ON squared. TLE, it's ON squared, right? It's ON squared. Given that n can be 3 times 10 to the 4th, I expected. It is not surprising. It is not surprising that this solution times out. All right, let's just take a look. Given how fast we get a response, it feels like okay, we passed quite a few, but we failed. So basically the question is, how do we make it faster? I mean, the slow part, right? What is the slow part? The slow part is for every node, we have to go through the entire thing. I mean, we can make it simpler. Hold on. Let me think. Let me think. So for each node, we will go through everything that's seen before, right? If we go only one of them, gracias, Miguel. Mi estómago ya está lleno. Ya está lleno desde la mañana. Brownie en la mañana. All right, back to this. So we're trying to reduce the number of computations, right? So here is the thing. For child in this and for ancestors in C. So what we can do, because we already know all of these are exactly the same, right? So we just need one of them. We only need to compute one of them, and everybody else can be the same. Then you have to update. We still have to update every single. So that. Hold on. Let me think. Let me think. What I'm trying to say is, it is the same from each child to everybody else, and for this to everybody else. So they're all the same. But then we do have to update this, right? Can we do better? Like literally, can we do better? Huh. Child, right? For each child, and then how to compute everything in the scene. And then after I compute everybody in this scene, I know for a fact that its sibling will have the same values. So technically we don't have to compute the siblings, but we do have to update the siblings. And if we update the siblings, it's the same thing. So we have to go through every child, right? We have to go through every single scene, and we have to update each child to the ancestor, each child to the ancestor. How can we avoid this? I mean, for one thing, right, like these three, we only need to compute 3 because they are all leaf nodes. So they will be exactly the same as this. Right? Right? Yeah. Alright, so what are you saying? What I'm saying is, what am I saying is, if I am a leaf node, right? If I am a leaf node, hold on. Hold on. It's not the same yet because they are not in scene yet. Hold on, so we get these out, right? We get these out, and then we do the computation with, but we don't know, gosh, we get 3, 4, 5 out, right? And then we can add the link to this, right? And after we add the link to this, yeah, we add their links, and then we pick one of them, and that one will be the one to compute the distance between this to everybody else. So 3 to everything else, including these, right? So like, they will be in scene. So these are everything in scene. And then we compute from 3 to everybody else. And if 4 is a leaf node, then we don't have to compute. We don't have to compute. 4, the result will be exact same as 3. Right? 5 is the leaf node, 5 will be exactly the same as 3. But if they are not the leaf node, then we still have to go through the entire same thing. So we can cut down some time, right? So like we don't have to, if we have multiple leaf nodes, then we only need to compute one leaf node and everybody else will be the same. But if we don't, and they still need to have their matrix populated. If they don't have their matrix populated, then it's not going to work. Now the thing is, once you get there, but that's the thing, right? It will be exactly the same. Like even if we get their leaf node, like what we're trying to say is if I have another value here, right, we're going to say, what is the distance between this, let's say towards 3, and I will go look at 4 towards 3, and that will be the same. Are you saying the same as 3 towards 3? See, that is the difficulty, right? That's the difficulty right there. That's the difficulty. What we're saying is, if they belong, like if we have these on the same level, and then their relation to the ancestors can be represented by one node, like one node. This one node can represent all the relationship, because that towards the ancestor is exactly the same as this towards all the ancestors. Now the problem with that is we use one representation for all the children, right? One representation for all the children. So if I have the grandchild, and I want to know the grandchild to like everything in the grandparent, so I can use one representation. And if it's another one inside, then that's just plus 2. Which means we only need one representation for each child. Think about this, one representation for each child, which means that will be condensed into one node. That will be condensed into one node, right? But if I have something here, they will be condensed into one node, like one representation. And they will be condensed into one node. I'm still trying to figure out how the structure is going to work. We're going to condense. We're going to condense the children of a parent into one node. I think by doing that, we can reduce it to what? O(n) log n? How do we condense? So the same thing, right? The same thing. We got. So basically, what we're saying is, from this, we look for the parent, and the parent will refer back to a child, right? We'll refer back to like a representation of all the children. And then it's from that children to everybody else, right? To everybody else. Which is fine. From that children to everybody else. That children to everybody else. So basically saying these two are the same thing, right? There's one entity. So this, I look here. What about scene? So what is scene? Are we not going through every single... We are going through every single nodes, but after we go through every single nodes, then they're all the same. Hold on, let me try it again. So I have 1 and 2, all right? Let's say we can condense them. So I go say, I want to know from 3 to 0. So I look for 2, and 2 belongs to this entity, and this entity has the same distance. to everybody else, right? So we find this entity, and it's going to be this entity towards all the other entities, right? So this entity towards the parent entities. But how can you do parent entities? It's not going to be parent entities. It's going to be individual, right? Individual node. So we're still going to maintain individual node, but that's just going to be one entity. Let's say we have one entity, and then we have this entity with everything, right? Everything. We have computed everything. Now, from 3 to everybody else, I go through every single thing, right? And if that thing is in scene, but it's not an entity, then we're going to refer to the distance between the entity towards that thing, right? Between the entity towards that thing. Okay, I guess. Between the entity towards that thing. Okay, so we have, do this again. So we have an entity towards everybody else. And then we're gonna get, so that's this entity towards everybody else. Okay, I guess that's fine. But how are we going to compute the distance? Oh, man, this is we have an entity that represents all the child nodes here, right? And then we can use that to compute everything. So that relates to this entity. And then within this entity, we don't have to compute anything because we can just calculate it. Right? Mathematically, we can calculate it. That's not an issue. Okay, so we compute this to everything. So the entity is the representation. And then we add this entity to the scene. Are you kidding me? Are we going to add the entity to the scene? Right? So the next one come out. Right? So this is an entity. Well, the children is the entity. So what we're saying is we'll compute the distance between the entity and the other entity. Between the entity and the other entity. How does that work? So we have this child, and its distance between this entity to this entity is, you're telling me these two things are the same, but they are not. They're not the same. No, they're not the same. From one entity, I cannot compare that to another entity. It has to be individual nodes. And if it's entity towards individual nodes, we still have to go through individual nodes, right? And from this, we have to go through individual nodes. But within this entity, we're only going to compute it once. That is the advantage. But after we computed it, we still have to update the matrix, right? Yeah, I think we still have to update the matrix. How do we update the matrix? Are we not updating the matrix? Hold on. Now we don't have entity. I know from, because this will connect back to this, right? And then we say this is inside the entity, so we go from the entity towards everybody else. And then we make the update for the entity, right? The update is based on entity. Okay, so this one will go to all the entities. But we still need to know just like the entity within this and the parent, right? This and the parent. What I'm saying is if I have another thing here, right, then I'm going up. I'm looking at this whole thing as an entity. And it's from this entity, because it's the same, like if I go 4 to everything else, it's the same as going to 3 to everything else. What I'm saying is 3 and 4, 5 can be combined together as the same entity. Okay. Hold on. What's the difference between 1 and 2? 2 has all this thing. So if we'll have children, right? And then if I compute one child, and I go to the other child, so they have the same distance to the ancestors, but they all have different distance to the two children. And when we consider 1, it's just going to be 2 to all the children, and then 1 is plus 2, right? What are you saying? What I'm saying is, if we get the distance, right, from zero to one, 0 to 2, to the 0, right, and then 2 to everything else. So it's like more, what's it, individual distance? Like, what if the distance, right? What if I like compute the distance on one level, right? Let's say on one level, right? And then from this, I compute the distance from one level. Hold on. we're trying to reduce the amount of computation, right? Amount of computation. So what we have here is what I realized, right? Is if I know 2, the distance between 2 and everything down, all right? Like if I do a recursion and I'm looking at 2 and I can obtain the distance from 2 to everything, right? 2 to everything. And then the distance between 1 to everything can be easily obtained, right? So all I need to know to get 1 to everything is 1 and adding 2 to everything plus 1 to 2 plus 1 to all the ancestor, right? That's how it is for each node. So for each node, the distance is going to be the distance of its sibling to all the siblings' children plus 2, right? And then each node to all the siblings, and each node to all the ancestors, and plus everybody else, and they can all be considered ancestors, right? Which is the distance between the root to everybody else. Not really the one that I was thinking about. Because I think I'm now looking more like a DFS, not like a BFS. We're looking at a DFS kind of solution. So like we only compute as 2 as a root to everything, right? But that's what we get. So 1 as a root to everything, 0 as a root to everything. And we can get a matrix out of it. We'll have like 0 to 1, 0 to 2, right? And 0 to... So by the end of the day, the root we choose, we have all done. And then from this, we have from 2 to all the... Yeah, 2 to everything else, but we don't have 2 to all the ancestors. That's the information we don't have. But we can reconstruct that information. We can reconstruct, right? So we have 2 to everything else. So we have the root. Root is going to be to every single thing, right? 1, 2, 3, 4. Right? We have every single thing for root. Now for 1, we only have 1's children, right? That's what we can have. So 1 to them, also to 1. That's what we can have. But then, if we want to know, right? So 1 to its children, they are done. But how about 1 to somebody else? Let's say I want to find 1 to 0. That's done, right? Well, if I want to find 1 to 3, right? 1 to 3. Then I need to find a 2, because I know 2 has 2 to 3. That is, so we go look at 3. All right, we go look at 3. 3 is connected to something. Like 3 is connected to 2. And then if I look at 1, 1 is also connected to, 1 actually does not connect to 2. 1 is connected to 0 only, right? And 0 is connected to 3. Okay. Hold on, what are we saying? What we're saying is from the root I have the connection to everybody, right? I have a connection to everybody. And so we have everybody to the root. That one is done. So if I have another node, because they only know its children, which is done. So if I want to find something else, so what I need is I can always go to, yeah, hold on. This is what I'm thinking about, right? I am a node, right? And then I want to know the distance between me and some other nodes, right? Some other nodes. Now that other nodes can be anywhere, right? It can be anywhere. So all I know is to get to that node, I need to go to my parent, right? So all I need to find is how can my parent go to this whatever other node. And that has already been calculated because if that other node is more parent, then that one to this is computed. We have it. If that node is to the children of that node, it's already computed. So that's how I know from this to that. We are good, right? So we can run on with each node visited once to get the distance from each node to all of its children, right? And then we can do the reverse thing as well. So from each node to all of its children, and because each node is visited once, so that is a on process. After that, we need to reconstruct for each node, right? So if it's the root node, so we just kind of go, then how do we know which one is which? So we go from root, right? And root is good. We don't have to handle anything at the root level. And hold on. So we add this, right? And then blah blah blah, we do recursion, whatnot. And then for each one, we are going to go left and right, and then we're done, so that's that. And then I return, right? This one I already return. And then we go the same thing one more time. So we do the DFS twice. The first time we populate the dist matrix. But that dist matrix is just from this one to everybody else. Now the second time when we do it, if I'm the root, right, and I need to look at my parent, but I do not have parent because that's when I start. There's nothing in the scene, right? So I don't have parent. Then I will take everything I have, so that would generate my result, and I go to my child, right? And for my child, I'm going to take whatever I have so far, right? Whatever I have so far, which is good, and then I'm going to go to my parent, and from the parent to go to everybody else. That is not my child. Okay, so from this to everybody else, that is not my child. Hold on. So from 1, I have a sum already. This sum is the total distance from 1 to all my child, right? We have a sum that's pointing to 1 is the sum of the distance between 1 and to all its children. Now I want to know what's the sum of distance from 1 to everybody else. So we look at its parent. It doesn't really matter parent. We look at the other node, right? So we look at this node, right? Then I just want to know the sum of this towards all of its children, all of its node. Now, when we consider this to all its node, we have a sum already because this is the root. I have its sum, the total sum. Now its total sum will include this and this, right? But what I want is this and this. So I just need to have this total sum minus this sum, right? And then minus this. And its total. We also need to know the number of nodes, number of children, right, that each node has. And that will be the, the total number of this we have to include, right? So if I say I have 2 children, so this one will count it twice. And adding this will count it 3 times. So what I need to know, it's the number of nodes on, let's say, on this side of the child. And yeah, so for this, we're going to have this, the entire sum for its parent, minus the number of nodes, which we can easily compute, right? We can easily compute. And then that's the number of times this repeats. And the total sum of this, that will be the sum of the distance from this towards everybody else on the other side. And then for 1, I simply add this total sum, right, and the number of nodes in there, which is the total number of nodes minus this. So that's the total number of nodes here. And for each node, I will add 1 and add this sum. So that's 1 towards everybody else. And we're good. Now I come to 2, right? 2, I have this one already, so we're good. And then 2, we go to its parent, right? Its parent. We go to its parent, and how are we going to do this? We'll do its parent, and the same thing. We're going to compute so 0 to everything here, right? So it's going to be the total this minus this and minus this will be total number of this, and then will be 2. We'll be adding this, right? Or to add this, then we have 2 to everything else. Now we go to 3. It's the same thing. Now we go to 3. So its children is 0. We don't have anything. So we're just going to go 2 to everybody else, which we already computed. So it's ON. It's ON. All right, let's try this. All right, I know it's late, and I already, I usually say like I will give up after 1 hour, but I see the light at the end of the tunnel for this one, so I'm gonna give it another shot. All right, so what do we want? What do we want is we need to get the tree for sure, so we need this. I doubt we need a distance matrix because we're dealing with sum, right? We're dealing with sums. So here's what we're going to do. What we're going to have is the result is going to be 0 times n, right? So that's going to be the result. Now, we're going to have a DFS, right? So we're going to have the node, which is going to be int, and we're going to return an int. So what it's saying is the total sum of the distance from me towards all my children, right? So here it is. If so what we're gonna do what we're about to do is I'm going to look into my child, right? So I'm going to look in my child. I say for child in tree node. Do have to use a scene, right? We have to use a scene so we don't go back. So for each node, we put scene.add node, right? So we add the node into the scene, right? And then we look at my children, right? Look at my children. If child not in scene. So I shouldn't say call it DFS. Let's call it dist from root, right? So if child is not in scene, I need all the distance from this towards everything, right? Towards everything. But I actually need two things. I also need the total nodes, right? I need two things. One is the total nodes, right? From this, we have the total number of nodes. Yeah, from the child. I want the total number of nodes and the total number of distance. I need two things. Right? I need two things. Therefore, this is not res, right? When we start, it is going to be actually, let's pass in that scene. It's going to be a set. So this is going to be a so what do we want? What do we want? What we want is from each root, I don't know how many children we have, how many children I have, the number of children I have, right? And the total distance I have towards those children. So it's two things. So let's say a dist root dist and count, right? That's going to be a list. Dist and count. So first of all, we're going to add this, and this one I'm going to return a tuple, right? We're going to return a. We actually don't have to. If we're going to record it in dist and count, then we can just return a none, which is totally fine, right? So if child is not in scene, we're going to do dist from root, child, scene, and dist count. Now, after that, scene is a set. And that's also a set, right? And this is going to be a list of list, right? So dist from root, we call dist from root on the child, right? Which gives me, if I look into the child, right? Look into the child, I'll have the total number of the distance and the total number of my child has, right? So after doing that, what I am going to do is do dist count, right? Dist count myself, which is node, right? And then that is a 0 is going to be, let's say 0 is the total distance, and 1 is the number of child, right? So 0 is the total distance, so total distance is going to be, the total distance, so going to be plus equal to right, plus equal to discount child, right? So discount child 0 is the total distance from the child to everybody else, right? And then what I need is this plus discount child 1. That's the total number of nodes my child has, right? And then we need plus 1 because I need to go to my child as well. So that's the total number. This is the total number of node, including my child, on that branch. On that branch. So what we're going to do, we're going to first update. So discount current node 1 plus equal to this. Oh, no, not this. Plus equal to this, right? So that is the total number of children I have on that branch. And then we're going to do this as well. So that is the total number of the total distance, right? From my children's distance, like the sum of distance to everything, and then we're going to add the total number of nodes, because that's how many I have to go at 1, right? Okay, so that's updating this. Then we're going to update this for every single child I have, and once I'm done, I don't have to return anything. It's just, like this, right? I would like to just mention, so discount I is total distance and number of children. Total distance from I to children, and total number of children. So let's make this and this. Right, so that's what it is. The total distance from I to all the children, and the total number of children of I. Right, that's what this count is. So when update the total number of children, which is my children's children plus my child, the distance will be my child's distance plus the total number of children my child has, like on that branch. So that's that. So once we've done this from root, we'll have the dist count. Now we're going to do one more. So def, let's call it solve, right? Let's call it solve. So we need a node, int. We don't need a scene, I suppose. But we do need parent. We do need a parent, right? So parent is going to be an int as well. So we need my current node. I need a parent, and I need the dist count. Right? I need a dist count, and this also going to return nothing, because I am also going to have the rest, which is going to be a list of int. And this count is still a list of int. All right. So to solve it, I'm going to go to the parent first, right? So the parent, when you say if parent is smaller than 0, then res node, basically just the root, is equal to res node equal to discount parent, no, discount node, total distance, 0. Done deal. Else, now we have a parent. Now we're going to have to, so res node plus equal to, yeah, plus equal to discount node 0, right? We have to do this first, which actually mean we have to do this no matter what, right? So we're going to do this no matter what. And then we just say if parent is larger equal to 0, right? Then we have to do something else. So we add node 0 is all the distance to my child, right? So now we want to know is my parent's distance, right? It's my parent's distance. How do I know my parent's distance? So we have parents all the distance, and we're going to minus everything that's on my side, right? How do we do that? So the parent distance is going to be discount parent 0. That's the parent distance. And we have the parent distance need to minus all the distance on my side, right? How to compute all the distance on my side? That's going to be discount node 0. That's my side plus all the children's I have, right? All the children's I have, which basically means discount node 1. That's all the children's I have, and plus 1, that's myself, right? So that's the distance between my parent to everything on my branch, right? So if I do the parent's total distance minus the distance from the parent to my branch, you see these two are exactly the same, right? If I do that, then I get the distance from my parent, right, to everything on the other side. So I get the distance from my parent to this, from parent to this, blah, 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 blah. Okay, right? So that is the distance from parent to everybody else, right? And then on top of that, I need to know the total number of nodes that they have, right? Which that node, so this is going to be other dist going to be this, right? Other dist, which is so be parent. Hold on, should be parent. The distance from parent to everybody else. The sum, right? So it's the other distance. So other distance is other dist is the total, is the sum of dist from parent to from parent to the nodes that are not nodes children, right? So we get the other distance, and now I need to find out the number of nodes that is in here, right? So we can say res node will be plus equal to other distance plus, right? What's the other distance plus the number of nodes that's in there, including this, which we can obtain by finding the number of I have, right? Number that my parent has. Number that my parent has, including everything, and I then minus the number that I have. So it's gonna be, yeah, just gonna be n, that's the total number, minus the number I have, which is dist count myself. 1, that's the number of node I have, right? And then minus 1, that will be all of this. And I need to add this value because of I have to count this thing. So I have a total of this, and I need to add to this, and then to this, to this, to this, some number. So that's the node. This. So if parent is larger than 0, we're going to do blah and blah, and then we're done, right? Yeah. Okay, now I'm done. So basically, I'm saying if we come from parent to node, right? And then when I'm done with myself, because the parent is done, and I'm done with myself, and then what I am going to do is to go to my children, right? So I'm going to go to my children, so it will be for child in tree node, right? I'm going to go to my children because I am done, right? I'm going to go to my children. I just realized I need scene as well for this to work. I need scene, which is going to be a set. Right? Be a set of int. I should do that. Set of int. So now I'll go to my children, and actually, every time we visit it, we have to say scene.add node, right? Now I want to go to my children. We say if child not in scene, right? So child not in scene, so I have my child. What I'm going to do is I'm going to just say solve. Child is the node. I'm the parent. Scene, pass in, dist count, I cannot change anything, and we're passing result as well. We're passing result, right? We're passing result. And we're going to solve for the child can be solved because I am solved. And then this child can be solved because also I am solved. I'm going to solve everyone, and then we're good. So we have two functions. So first, we're going to call dist count equal to 0, 0, right? 0, 0 for this range n. It's dist count, and we're going to do dist from root. 0 is our node, and then scene is just going to be a set, and dist count. That's the first one. We have the dist count, dist from root, and then we're going to have res equals to 0 times n, right? Then we're going to call solve 0, parent start with -1, scene is a set, and dist count, use it, and res, right? So we're going to solve it. And once we're done, we're going to return the res. All right, just give this one a shot. This is solution 2. We passed the second one, we failed the first one. We almost All right, we almost got the first one. Let's see, what did we do wrong? Okay. Let's find out the dist from root. No, let's find out the dist count. We don't have to do these two. All right, this is the dist count. So from the 0, we already have 8, and we have 1, 2, 3, 4, 5. That's fine. And 1, right? That's 1. 1 has a 0 and a 0, which is true. 2, right? That's 2. We have 3, 1, 2, 3, and 3 nodes. And 3 is 0, 0, 0, 0, 0, 0. Okay, that's fine. This count is fine. Now I'm going to go to here, right? So 8, perfect, because that's that. And then the children, we have 1 and 2. So we go to 1 first. I'm going to solve 1. Now solve 1, we got 12, because 1 is actually right? So we have 1 is 0, so other distance is going to be the parent 0, which is 0, and a minus, the parent is this, so 8 minus 0 plus 0 plus 1, minus 1, so it'll be 7, right? 7, which means other distance is 7. The total distance here is 7, which is true. And then rest node would be 7 plus the number of nodes. So n is 6 minus node, it's a 0. So we go to 3, right? And 3, we're going to add itself, which is 0. And then we go to parent, right? So we say we go to the parent, and then the parent is 0. That's not parent 0. Is it? No. No, that's not parent 0 though. That shall be res parent. That's res parent. That's a res parent. Because that's total minus, right? That's the total minus on this side, right? Minus on this side. That's the other distance. So if we run this, now we pass, right? So now we're going to do this and delete this. Run it, we pass. Oh boy, let's try this. Let's try this. Oh, I'm excited. Okay. Let's run this, and let's see how fast we got. Run code. Finished. 112 milliseconds. I don't know if it's fast enough, but we can try. Submit. Pending. Judging. Accepted. Accepted. O-N. O-N, baby. O-N. Let's take a look. We are somewhere in the middle. Somewhere in the middle, right? Somewhere in the middle. Nice. Nice. I feel very proud of myself. So we came up with 2 solutions. This is ON. I'm very, very sure that this is ON. Because basically it's 2 DFS, right? 2 DFS and each child gets visited once. Alright, so here is the thing. So this one, I'm very proud of myself solving this one. So the idea, we run 2 rounds of DFS for this. The first round, DFS, dist from root, we compute the total distance from a node to all of its children, and we also count the total number of children a node has, which I just realized can be achieved differently. But like we can go this, we know the total number of children, but because that's including the node, including the maybe we can do it differently. No, let's just do it this way. It's easier, right? It's easier. All right. We also count the total number of children a node has. The second round, BFS solve, we compute the total distance for each node. Now the main insight in this round is that given a node and its parent, the total distance is the sum of the nodes, sum of the distance from the node to all its children, and the distance from the parent to the distance going from the root from the node to its parent, and all of the distance from the parent to the nodes not in other than the current node and its children. To put it in an expression, if we have how do you say that? If node has total the distance going from the node to its parent and all of it. So if when we solve a node, it is guaranteed that we have already solved the total distance for its parent. So given node as parent, the total distance is the sum of the distance from the node to all its children. This is trivial, as it has already been computed from the previous, right? From root, right? Computed by dist from root, and the distance going from to all of blah 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 blah. I'm trying to explain what this means. This node and its children. Let's call this other dist, right? And when we solve a node, it is guaranteed that we've already solved the total distance for its parent. So to compute other dist, we do total dist from parent, right, minus the total distance from parent to the branch that includes the current node. Right? That's what it is. Now to compute the total distance, right, from parent to the branch that includes the current node, so that includes the current node, the total distance from the parent to the branch that includes the current node is the total distance from the current node to all its children computed already by dist from root, and the total number of nodes on this branch. This can be computed indirectly computed by dist from root as well. All right. So there we have it. There we have it. 2 rounds of DFS, both ON, because each node is visited once. So total time complexity is ON, and we run it at 1,100 milliseconds, or a 26% ranking. I'm pretty sure the good solutions, look at the good solutions. All right, anyway, so let's take a look at solution. That's a good question. It's a very, very good question. So TLE, so this is a BFS, BFS based solution. And this is it's pretty hard. It's actually very, very hard. LeetCode 834, right? Yeah, 834. Oof. This is a good question. Which one subtree, sum and count? ON. All right. One of the best. Yeah, this is a good, hard question. It doesn't really matter. Anything can be a root. Yeah, root is irrelevant. All right. All right, let's take a look. It is 2 rounds of DFS. 2 rounds of DFS. Yeah, I think we got it. Right? You see count children, n minus count children. All right, let's just see. So we use count and then answer. I think count. So we do this already. So instead of having this, we do it already. Node parent. So if a child in node, if child is not parent, if child is not equal to parent. Oh, we don't have to use seen. Oh, we don't have to use seen. Well, the reason we don't have to use seen is it's a tree. So we only need to check the child is not the parent. Yeah, because we go as a tree, so it's go level by level. Yes, okay, so that's a good improvement. If child is not equal to parent, so we DFS child and node. So this is compute. What does this one compute? This one compute the count, right? Oh, look at that. The answer is already there. So we count as the count number of child, and this one will be answer of the child plus the count of the child. I can count as the total node that including the child. Yes, this is the branch, the current branch. And then we do it again. So answer child will equal to answer child. If child is not equal to parent, so answer child will equal to answer node. Answer node minus count child plus n minus count child. So let me just go through the mind one more time. So the answer child, right? We're updating the child first. Hold on, we are at hold on. We're at the node, right? So we add the node and we're going to the child. And then what I'm saying is answer node is already done, right? Answer node, we're saying the answer node is already done. So the child will equal to answer child. Shouldn't this be plus equal to? I don't know. Because we have answer child already. So we say answer child will equal to answer node, as a total, minus count child plus n minus count child. All right, this one I'm got a bit stuck. I don't understand this one. Answer child. We already have something in answer child. Don't forget, we already have something in answer child. Answer node. That's the total, right? And then we're gonna go for the child again. Child is the next node. So this is to prepare the child. Okay, this is what I see. This is to prepare the child. Now, how do we prepare the child? And then we go. No, this is to compute everything, right? Let's see. Right, it's parent of the child. Count child. Answer parent. That's the total. That's the total distance, right? The total distance. So child equals answer parent minus count child minus count child. So we have the total distance from this towards everything. So from this towards this, right? So we have this towards this and this towards this. So what I want is from this towards everything. So that this towards everything here and this goes in there. So this goes in there is n minus count child. Yes, n minus count child is everything. We have to add that. and that's that part. Okay, so the total distance, right? The total distance to that part, adding this, and the total distance to this part, we need to minus, because we don't have to go through all this. Ah, I see. I mean, I got it, right? But it's a little bit more convoluted than the way that they're done here. Ah, answer node minus. So this is the total distance, right, from this child to its children, and from root to its children, to the other. So this is the other distance, and this is this. So this distance plus this distance is answer node minus count child. Brilliant, brilliant. Yes, yes. Because that's the total distance, right? The distance from this. So we just minus this, that's yes. And then plus and minus this, we kind to add this one. Ooh, nice, nice. But we did get there, right? Just not as nice as this. So let's just, I'm not going to redo it because we are very, very close. Right, I'm saying very close. So, date. We are very, very close to the official solution. The only thing that we lack is brevity, right? It's brevity. We use more space than the official solution, and we use more space because we fail to see that I shouldn't say fail to see. We failed to see. Well, we failed to see two things, right? Two things. First, the set scene is not needed because we are handling a tree. All we need to do to prevent revisiting node is node not equal to parent. And two, the dist count can be decommissioned, can be split into node count and distance count. Node count, right, and then distance count can be reused as res in the second round of DFS. The key insight for this reuse is that res node equals res, right? Res node equals res parent minus count node plus n minus count node. That's the key. That is the key insight. We have discovered, right? Discovered n minus count node ourselves. But here, the important, but here, res parent minus count node, right? Minus count node represents the total distance, represents the sum of the distance between of, how should I say it? It represents the distance from node to its children plus the distance from parent to all the other nodes, that is other dist. It's it is a better way than calling is a better way than calling, for us is going to be dist count node, then calling this, right? Then calling this plus this other dist. This is what we have. But I don't know, I just end it here. It should be good enough. Wow, what a ride! What a ride! What a ride! That was good that we stuck with it. Yeah, it's a pretty hard question. Pretty hard question. DFS is ON. Wait, is this like a Google interview question? Reading, intuition. Oh, he just say greeting to his mom. I mean, now I want to like kind of summarize, right? So when we first see this question, I know that we have to reuse things, right? The things we computed before we have to reuse, and there's a lot of recursive relations in this. So I think the first intuition is because if I know the distance from one node to the other, then I know the reverse, right? So the first intuition is if I think of this in a BFS kind of way, we go layer by layer, right? Then from each node, if I know the distance to everybody in the previous, then the children can be computed easily because I know the distance to everybody else through my parent, right? Because I know the parent to everybody else, that has happened before. So from me to everybody else, it's just going to be me to the parent, and the parent to everybody else. And everybody else is already cached. So that's the first solution. But it's O(n) squared because we must compute each pair. Right? So that's O(n) squared. And it's shorter, right? O(n) squared. So then we have to think deeper, because to do it O(n), that means we have to take advantage of the sum already. So we cannot do every single pair. So if we cannot do every single pair, the next intuition is, okay, BFS will try, so we just let's just do DFS, right? And DFS is a tree, so naturally we think we just take a look at the node and then treat each node as a root, and then we get the sum of all the distance of its children, right? So that's a sum. So now we start thinking like that, right? Now we think like that. So we notice immediately the root, we already computed everything, right? And then I look at 1, right? And we say, okay, 1, I imagine we have some nodes. So I say, okay, we already computed the sum, so we have some sum. So all the sum we need is the distance from 1 to everybody else. Now to get 1 to everybody else, I realize we have 0, its parent, to everybody else, right? So to get from 1 to everybody else, all I need to find is the distance from 0 to 1 and its children. So this branch, because we want the distance of this branch, and we know the total distance from 0 to everything. So all we need to know is from 0 to this branch. And surprisingly, we do know because we know from 1 to this branch. We already computed. So to get this, all we need is from the distance from 0, right, to everything, minus this branch. And this branch includes this part and the total number of nodes, right? And then if we remove all that, now we get this, and that is what we need to add to this. And of course, we also have to add the total number of nodes here, because we have to go 1 to every single thing, and that's the solution. Now, it is easier, right, to get that from this. So that's the intuition I did not have. That is, if we do total minus the number of counts, we immediately get the distance from 0 to everything here, and 0 and 1 to everything here. All right, that's immediately we get from that. So we don't have to use the ones already computed. So that's the intuition I don't have, which is actually very nice. Yep, that's the whole process. But no, I think, no, I don't think I can solve this in 45 minutes. This is pretty tough. All right, that will be it for today. I'll see you guys tomorrow. Adios.